Hi, my name is Brian Hugh. I'm a senior R&D engineer at Kitware, and today I would like to tell you about our work on explainable medical image retrieval. Taking the example of chest x-rays, machine learning models can now provide automated diagnoses by answering questions such as, what pathology is this? In this case, the model predicts pneumothorax or a collapsed lung. However, oftentimes it is also useful to know why the model predicted pneumothorax. This is where explainable AI comes in. We can use saliency maps, which are a form of visual explanation that reveal parts of the input image the model paid attention to when arriving at its prediction. Here, the saliency map shows that the model focused on this lung region. In contrast to image classification, our work explores explainable image retrieval. Here, the model aims to retrieve similar images from a large archive given only a single query image, such as the one shown on the left. The retrieved images can facilitate case-based reasoning and the discovery of underlying patterns in the data. We can also use similarity-based saliency maps to reveal parts of the retrieved images that match the query image and were used by the model during the retrieval process. Our overall approach is summarized here. Using deep metric learning, we learn a lower dimensional embedding space where different conditions can be easily separated. At test time, given a query image, the model retrieves the most similar images from the archive, shown here in the upper right. We can also compute different types of similarity-based saliency maps to provide a form of model explainability. To evaluate these saliency maps, we can compute the metrics of insertion and deletion. In our work, we focus on two different medical imaging datasets. One dataset involves chest x-rays, including those with COVID-19. The other dataset involves ISIC skin lesion images, including those with cancerous melanoma. Our image retrieval results are shown here. We report the standard metrics of mean average precision and precision at K. We use a DenseNet 121 architecture, which is trained with deep metric learning and a triplet loss. We emphasize that our goal was not to obtain state-of-the-art performance, but instead to create a set of baseline models with which we could compute and evaluate saliency. Qualitative results in the COVID-19 dataset are shown here. Query images are highlighted in blue, the correct matches are shown on the left highlighted in green, and incorrect matches are shown on the right highlighted in red. Retrieved result images are presented along with their corresponding saliency maps for each of the three different conditions. We also obtained similar results on the ISIC 2017 dataset. Interestingly, for both datasets, we found that sometimes the model focused on the correct regions, such as the lungs or the lesions, even when it returned incorrect results. This highlights the need to go beyond simple qualitative comparisons and to develop more quantitative metrics to evaluate these saliency maps. Towards this end, we adapted the insertion and deletion metrics introduced in the RISE paper for image similarity. Taking deletion as an example, we iteratively mask out regions of the image based on their relative importance from the saliency map. A good saliency map will show a rapid drop in image similarity, as the most important pixels have now been removed by this masking. We can quantify this by computing the AUC as a function of image similarity and the percent of pixels perturbed. Computing these metrics across the two datasets revealed that the different saliency algorithms perform better for different datasets. Critically, the saliency maps were also sensitive to random initialization of the model weights, which passes one of the sanity checks for saliency maps proposed by Adebayo et al. In their paper. Finally, we developed a form of differential saliency, which can highlight which image features were more likely to correspond to different conditions. In the first row, we show the average images separated by condition. In the second row, we show the average self-similarity saliency maps, which reveal condition-specific image features used by the model. In the last row, we show the differential saliency maps by taking differences in the average self-similarity saliency maps. While these results are preliminary, we hope that this is a useful tool for more detailed analyses of saliency maps. Thank you for your time and attention, and feel free to explore our open source code using the link below.